Hello, today I'll be discussing the properties and behaviors of two important polymers used in pharmaceutical formulations, Carbomer 940 and Poloxamer 407. Specifically exploring how pH affects the viscosity of Carbomer 940, how adding solvents such as ethanol and water alters the viscosity, the shear thinning properties of Carbomer 940, and the thermal-reversible gelation of Poloxamer 407. Now I'll discuss the effects of pH on 0.65% Carbomer 940 viscosity. Carbomers such as Carbomer 940 have a pKa of approximately 6.5, classifying them as a weak acid. This is important because of their ionization state changes depending on the surrounding pH, directly influencing the gel's viscosity. At a higher pH level where the environment is less acidic, carbomers tend to ionize more readily by donating protons. This ionization results in negatively charged polymer chains that repel one another, causing the gel network to expand and swell, in which viscosity increases. Conversely, at lower pH levels, carbomers remain largely non-ionized. In this state, the polymer chains are more compact due to the lack of electrostatic repulsion, leading to a minimal interaction between them and a corresponding decrease in viscosity. Thus, the degree of ionization in varying pH environments dictates whether the gel structure will expand, leading to the higher viscosity, or remain condensed with a lower viscosity. Carbomer 940 is sensitive to pH changes. The results show that Carbomer 940's viscosity is significantly influenced by the pH of the solution. As the pH increases, the carboxyl groups become ionized, allowing the polymer chains to uncoil and expand, which increases the gel's viscosity. At a low pH, these carboxyl groups remain protonated, resulting in a compact structure with low viscosity. However, as the pH rises and the groups ionize, electrostatic repulsion between the polymer chains occurs, further increasing the viscosity. At a pH of 1.49 using hydrochloric acid, the apparent viscosity of Carbomer 940 was extremely low at 6.9 centipoise. This low viscosity is due to the carboxyl groups remaining protonated in a highly acidic environment, keeping the polymer in a tightly coiled state with minimal interaction between the chains. As the pH increased to 4.46 using a phosphate buffer, the viscosity slightly rose to 65.0 cp. Although still acidic, this increase suggests that some ionization of the carboxyl groups, allowing for more polymer expansion and interaction. The most significant increase in viscosity occurred at a pH of 7.4, where it jumped to 1667 centipoise. At this pH, the carboxyl groups are fully ionized, leading to a strong electrostatic repulsion between the polymer chains, which causes the gel network to expand significantly, increasing the viscosity. Finally, at a pH of 12.04 using sodium hydroxide, the viscosity reached its peak at 8,383 centipoise. At this highly alkaline pH, the polymers remain fully ionized and hydrated, forming a highly viscous gel. Although extremely high pH levels could potentially destabilize the gel, in this case the viscosity continued to increase. Carbomer 940 has a backbone of carboxyl groups. At low pH, these groups remain protonated and neutral, limiting electrostatic repulsion between polymer chains, resulting in a tightly coiled structure and low viscosity. As the pH increases, the carboxyl groups deprotonate, forming negatively charged carboxylate ions. These negative charges repel each other, causing the polymer chains to uncoil and expand. This expansion traps more water within the gel matrix, leading to a dramatic increase in viscosity. Now, the effects of adding ethanol or water to 0.65% Carbomer 940 gel viscosity. Carbomer 940's viscosity is not only a pH dependent but also sensitive to solvent composition. Water promotes polymer hydration and can maintain viscosity up to a certain point, but over dilution causes a decrease. In contrast, ethanol disrupts the water-polymer interactions, causing a more significant viscosity reduction. With the impact of water, the apparent viscosity of Carbomer 940 gel was 7,817 centipoise. After the addition of water, the viscosity decreased to 6,167 centipoise. This decrease in viscosity occurs because adding water dilutes the concentration of polymer in the gel, reducing the number of polymer interactions. Although the water allows some degree of polymer expansion, too much water reduces the gel's ability to maintain its structure, resulting in a lower viscosity. When it comes to the impact of ethanol, the effects of adding ethanol is more drastic. Initially, the gel had a viscosity of 8,383 centipoise. After adding ethanol, the viscosity dropped significantly to 3,300 centipoise. This large reduction is due to ethanol's nature as a less polar solvent compared to water. Ethanol competes with water for interactions with polymer chains, disrupting the hydrogen bonds that holds the polymer structure together. As a result, the gel network collapses more substantially, causing a sharp drop in viscosity. These results highlight that water and ethanol have different effects on the viscosity of Carbomer 940 gels. With the addition of water, adding water to the gel dilutes it, decreasing the concentration of polymer chains. However, since water is a highly polar solvent, it supports the hydration and swelling of the Carbomer 940 chains. As a result, the reduction in viscosity is modest, the gel's network remains mostly intact and is less dense. Whereas with the addition of ethanol, as it's a less polar solvent than water, it disrupts the hydrogen bonding between water molecules and the polymer. This disruption breaks the interactions between the polymer chains and the surrounding water, effectively collapsing the gel's network. Consequently, there is a significant decrease in viscosity as the polymer chains become less hydrated and extended. Number 3, the effect of changing the spindle speed on the Carbomer gel's viscosity. Carbomer 940 demonstrates shear thinning behavior. We investigated the impact of spindle speed, which stimulates the shear stress applied to the gel, on the viscosity of Carbomer 940. The results demonstrate a clear shear thinning behavior, which is typical for non-Newtonian fluids like Carbomer 940. These results show as the shear rate increases, the viscosity of Carbomer 940 decreases. The results demonstrate the shear thinning or pseudoplastic behavior of Carbomer 940 gels. Shear thinning occurs when a gel's viscosity decreases with the increasing shear or agitation. As the spindle speed increases, more shear force is applied to the gel, causing the polymer chains to align in the direction of flow. This alignment reduces the resistance to movement, leading to a decrease in viscosity. Unlike Newtonian fluids, such as water, which maintains the constant viscosity regardless of shear rate, non-Newtonian fluids like Carbomer 940 exhibit changes in viscosity when subjected to varying forces. Lastly, the effect of temperature on 15% Poloxamer 407. Poloxamer 407 exhibits thermoreversible gelation, meaning it behaves as a liquid at lower temperatures and transitions into a gel at higher temperatures. This makes it useful in drug delivery systems that require a phase change at body temperature. At room temperature 25 degrees Celsius, the viscosity of Poloxamer 407 was measured at 170 cP. However, when the temperature was increased to 37 degrees Celsius body temperature, the viscosity drastically increased to 4,580 cP. These results show that the gelation behavior of Poloxamer 407 as temperature increases. As you can see, at 25 degrees Celsius, the viscosity indicates that the Poloxamer solution is still in liquid form, and at 37 degrees Celsius, the viscosity increases drastically as the solution transitions into. This behavior occurs due to an amphiphilic block copolymer structure of Poloxamer 407, which consists of hydrophilic polyethylene oxide and hydrophobic polypropylene oxide blocks, or PEO and PPO blocks. And at low temperatures, the PEO blocks are hydrated and the polymer chains remain dispersed in the solution, leading to a low viscosity. At a higher temperature, the PPO blocks become less soluble in water and begin to aggregate, forming micelles. In conclusion, when it comes to pH sensitivity, Carbomer 940's viscosity increases with pH due to the ionization of its carboxyl groups, making it a versatile agent for formulations requiring pH adjustments. And with the effects of solvent, water maintains some gel structure due to its polarity, while ethanol disrupts the gel network more, leading to a sharper decrease in viscosity. As for shear thinning behavior, Carbomer 940 gels exhibit a shear thinning, which allows them to be more spread easily when applied, but remain stable otherwise. Lastly, when it comes to temperature sensitivity of Poloxamer 407, the thermoreversible nature of Poloxamer 407 allows for the creation of gels that can transition from liquid to gel with temperature changes, making it useful in various pharmaceutical applications. Thank you for listening to my presentation. Here are my references.